We have seen that a moving charge creates magnetic field. But when we say moving, the obvious question is, with respect to what? If we are stationary, then the charge is moving with respect to us. But if we start moving with the charge, then the charge is not moving with respect to us. Since this equation involves the velocity of charge, and in this frame of reference, the charge is stationary, so in this frame, there will be no magnetic field due to this charge. This is what experimental observation confirms. That is, when we are stationary and the charge is moving, we perceive a magnetic field produced by it. The moment we start moving with the charge, its magnetic field disappears. More interestingly, if the charge does not move, but we start moving, we again perceive a magnetic field as that due to a moving charge. So does this mean that magnetic field is a relativistic phenomena? Yes, it is. In fact, even the electric field is not exactly what we have known it so far. When this charge is stationary, its electric field is what we have discussed before. But the moment this charge starts moving, its electric field also changes. Electric field of a moving charge is still radially outwards from it. But now it is stronger in a plane perpendicular to its motion. That is why we refer to the electric field of a stationary charge as its electrostatic field. An electric field of a moving charge is different. So is electric field also a relativistic phenomena? Yes, it is. In fact, both electric and magnetic fields are relativistic aspects of an electromagnetic field. In order to understand electromagnetism, we will need an in-depth understanding of Maxwell's equations and special theory of relativity. And both of them are beyond the scope of this course. However, even without going into the details of Maxwell's equations, we can see that a time variable magnetic field produces electric field. And a time variable electric field produces magnetic field. We will discuss more on this in the next chapter. However, for now we can just say that electric and magnetic fields are entangled with each other, and one changing field produces the other. However, if the fields are not changing, then these effects disappear and we are left with the equations of electrostatics and magnetostatics. This is what we have studied so far. In fact, theory of relativity tells us that the electric and magnetic fields transform into each other. Let us say we have a pure electrostatic field. The moment we move perpendicular to the field, a magnetic field appears and the existing electric field is reduced. If we have a pure magnetostatic field, then the moment we move, an electric field appears and the magnetic field changes. Since looking at a situation from a different frame of reference cannot change the fundamental nature of fields, so this tells us that electric and magnetic fields are just relativistic aspects of a single electromagnetic field. The situation is similar to a holographic picture, where we see one picture from one point of view and the other picture from another point of view. But overall, it is a complex entanglement of both the pictures. Similarly, what we may see as a pure electrostatic field in one frame of reference and a pure magnetostatic field in another frame of reference is actually a complex entanglement of both, which we call an electromagnetic field. That is, it is an electromagnetic field which is perceived as only electric and only magnetic field in special situations.